The Griffith Observatory in Los Angeles includes an astronomical refracting telescope, the Griffith telescope, with an objective lens diameter 305 mm and focal length 5.03 meters. Calculate the wavelength of light for which the Griffith telescope has a minimum angular resolution of 1.8 times 10 to the minus 6 radians. So the first thing to do here is to label the information that's relevant to us in the question. So this 1.8 times 10 to the minus 6 radians is the angular resolution, and the 305 millimeters is the lens diameter. Now the equation that we're going to need to use is theta equals lambda divided by d, where lambda is the wavelength of light, and the other two variables are given to us. So we need to rearrange this equation to make lambda the subject. So inputting our values. Now I've used 0.305 instead of 305 millimeters because we want to work in SI units. And that gives us a wavelength of 5.5 times 10 to the minus 7 meters, which is 550 nanometers. So that would be roughly green light. Now, in terms of marks for this question, your first mark will be for identifying the lens diameter and converting it to meters. And your second mark will be for getting the correct answer at the end. So 2 marks there. The Griffith telescope is used to observe 2-point objects which subtend an angle of 1.8 times 10 to the minus 6 radians at the unaided eye. The typical human eye has a minimum angular resolution of approximately 3.2 times 10 to the minus 4 radians. Calculate the focal length of the eyepiece lens so that an observer can just resolve the two objects when observing them through the Griffith telescope. Now, the first piece of information that we're going to need here is the focal length of the Griffith telescope, which is 5.03 meters. The equation that we're going to need to use is the magnification equation, which is equal to the focal length of the objective lens divided by the focal length of the eyepiece lens. But remember that Fi, or the focal length of the eyepiece lens, is what we're trying to calculate. So let's rearrange to make this the subject. Now we need to find a value for m, and that can be calculated by dividing the minimum angular resolution of the human eye by the angular separation of the 2-point objects. So combining all of this information together, we end up with 0.028 meters, which we can write into the answer space. The marks given in this question will be first of all for writing down the angular magnification equation with the necessary values. Your second mark will be for the use of the magnification equation in terms of the focal length of the eyepiece lens. And your third mark will be for getting the correct answer at the end. So 3 marks there. The asteroid Apophis has a diameter of 325 meters. It has been calculated that in 2029, its distance of closest approach to the Earth's surface will be 3.0 times 10 to the 4 kilometers. The Griffith telescope may be used to view Apophis using the eyepiece calculated in question 1.2. Deduce whether this telescope is suitable to obtain a detailed view of Apophis. Support your answer with a calculation. The first thing to do in this situation is use the values that were given, which are the diameter of Apophis and its distance from Earth's surface, as these can be thought of as lengths on an arc diagram. So when viewing this from Earth, we can see that we can calculate an angular diameter of this asteroid. So we would do this by dividing the arc length by the radius. So this gives us 1.1 times 10 to the minus 5 radians. You get a mark for making this calculation. We can then compare this to the angular resolution of the telescope, which we know to be 1.8 times 10 to the minus 6 radians. Now, we don't get a mark for saying this, but we do get a mark for comparing this angular resolution to the angular diameter of the asteroid. So for working out how many times the minimum resolution the asteroid's angular diameter is, which is 6.11, we get another mark. And then your third mark would be for stating that you wouldn't be able to see the asteroid in very much detail. Thinking of this view in terms of pixels, if the smallest we can see is 1.8 times 10 to the minus 6 radians across, then we're only going to see 6 of these smallest pixels of our resolution across the width of this asteroid. So it would be like viewing a picture that's 6 pixels across, so not very detailed at all. So those are our 3 marks. Sketch on the axes in Figure 1 the blackbody radiation curve for a typical star. So you can see Figure 1 here with a set of axes. The intensity is in arbitrary units and the wavelength doesn't have a scale, but we can still indicate the shape of the graph because this is only a sketch. So this is what the shape of the graph should look like. You'll get 1 mark for showing that the curve has a single peak, and this is at the wavelength that has the highest intensity. The second mark will be for having a right-hand side. Your second mark will be for having a curve where the steepest part of the left-hand side is steeper than the steepest part of the right-hand side. So we can see that on the left-hand side it's nearly vertical, but on the right-hand side it's not as steep. So 2 marks there. Explain, with reference to the SI units involved, how the curve you have drawn can be used to determine the blackbody temperature of the star. So you'll notice on that graph I talked about the most intense wavelength, but we're going to call that the peak wavelength. And that will be your first mark. Your next mark will be for mentioning Wien's displacement law and talking about wavelength being in meters. And that will be your second mark. The equation form of this law is lambda max times T is equal to 0.0029 meter Kelvin, where T is the temperature in Kelvin. So if you write this equation down with labels, then you'll get your third mark. You'll notice that when the constant that we use is 0.0029, its units will be meter Kelvin. So we have to use wavelengths in meters and temperatures in Kelvin. So that will be your third mark. 2 stars, 61 Cygnus A and 61 Cygnus B, can be seen very close together in the constellation Cygnus. Early astronomers were unsure whether the 2 stars form a binary system or simply appear in the same line of sight. Table 1 shows some of the properties of the 2 stars. So you can see Table 1 there with a row for 61 Cygnus A and a row for 61 Cygnus B. We have the temperatures in Kelvin, the radii in kilometers, and the apparent magnitudes. Evaluate whether the data support the suggestion that the 2 stars form a binary system. In your answer, you should compare the 2 stars as seen by an observer on Earth and support your evaluation with suitable calculations. So the first thing to do here would be to compare the color and brightness of the stars. So let's look back at the data. We can see that Cygnus A is 4,500 Kelvin and is therefore hotter than Cygnus B at 4,100 Kelvin. So let's write that down. You can also mention the peak wavelength, as we talked about in the earlier equation. So that's all we can say about color. Let's talk about brightness. The stars will have a difference in apparent magnitude of approximately 1, or 0.9 more specifically. So the ratio of the brightnesses can be calculated using the following equation. So the ratio of brightness is equal to 2.51 to the power of the difference in apparent magnitude. So from that we can see that Cygnus A will appear roughly twice the brightness of Cygnus B. So Cygnus A's brightness would appear to be roughly double Cygnus B's brightness, and that's because the value 2.51 to the power of 0.9 is going to be equal to 2.3. The next thing that we want to talk about is distance, and we're going to use Stefan's law to find the power output at the stars. So we've got the power output of the star multiplied by the Stefan constant, multiplied by the surface area, multiplied by the surface temperature to the power of 4, but this temperature has to be in Kelvin. So let's calculate those for Cygnus A and Cygnus B. So those are our power values. We've multiplied the Stefan constant of 5.67 times 10 to the minus 8 watts per meter squared per Kelvin to the 4 by 4 pi times the radius squared, which gives us the surface area of a sphere, multiplied by the temperature in Kelvin to the power of 4 in each case. So the power of Cygnus A is 6.45 times 10 to the 25 watts, and the power of Cygnus B is 3.38 times 10 to the 25 watts. Bear in mind that the radii of those stars have been converted into meters and are not left in kilometers. So what we can do now is link this to the brightness difference and make a judgment about the distance. So we're saying that Cygnus A is roughly twice as powerful and appears twice as bright. There are no variations caused by a difference in distance, and what I mean by that is if you take a source of light and move it further away, it will appear more dim. But if Cygnus A truly is twice as bright and it looks twice as bright, there won't be any effect caused by the two stars being at different distances from us. So we can conclude there that the stars are approximately the same distance away. All we need to do now is provide an evaluation on whether or not this is a binary star system. So my evaluation here says that if the stars are close in a constellation and at the same distance, it is likely that they form a binary star system. Now you don't need to mention that they're close in a constellation, but I thought I'd include that as extra evidence. If they were in opposite directions in the sky, then they clearly couldn't be part of a binary star system because we'd be in between them. But the fact that they are at roughly the same distance strongly suggests that they are part of a binary star system. Now to get 6 marks in this question, you need to have calculated the power outputs correctly, compared the brightnesses of the stars, and come to the conclusion that the stars are a similar distance away from each other. Now I'm not going to assign specific marks to this because the mark scheme isn't as simple as that. There's also a mark given for quality of written communication, but if I give you an example of something that might cause a mark to be lost, there could be an error in the calculation. For example, in a power of 10, you might leave the radii of the stars in kilometers by accident, for example, but that could drop you a mark. Further marks would be deducted from full marks for mistakes in calculations or wrong conclusions reached. But the mark scheme is the best place to look to work out how many marks a given answer is worth. What is the spectral class of 61 Cygnus A? Tick the correct box. Now the answer to this question is K, as this is somewhere in the region of 3,700 to 5,200 Kelvin. Now, you don't need to state this to get the mark, you only need to tick the correct box, but you definitely need to remember this for the exam. So 1 mark there. Describe the links between galaxies, black holes, and quasars. Now for this describe question, you just need to know the key facts about these 3 objects. Quasars are produced by supermassive black holes. You don't need to say supermassive, but you need to say they're produced by black holes. And that would be your first mark. Linking this to galaxies, the black holes that cause quasars are usually at the center of galaxies. And that would be your second mark. You can mention things like active galactic nuclei as being the centers of those galaxies, but that's not required for the mark. That's extra information. At a distance of 5.81 times 10 to the 8 light year, Markarian 231 is the closest known quasar to the Earth. The redshift Z of Markarian 231 is 0.0415. Use these data to estimate an age in seconds of the universe. Now, whenever a question is asking you to find the age of the universe, you need to do the inverse of the Hubble constant. Now, using the data that we're given, i.e. the distance of Markarian 231 and the redshift of that quasar, we can find a value for the Hubble constant so that we can find the age of the universe. So we're kind of working backwards here. Now, redshift Z is equal to the speed of recession of the quasar divided by the speed of light. So let's add some labels there. Now we could use this to find the recession velocity and insert this into the Hubble equation, but that would be 2 steps and it may reduce the accuracy of our answer. So what I'm going to do here is combine this equation with the Hubble equation, And you can see that that's where the Hubble constant appears. So combining those two equations together, we can obtain an equation which puts the Hubble constant as the subject. So the Hubble constant is equal to the redshift multiplied by the speed of light divided by the distance of the quasar. Now we could go a step further here and find the inverse of the Hubble constant so that we've got a direct value for the age of the universe. So all we need to do is do 1 divided by the Hubble constant, or flip the ZC over D fraction upside down. Then all we need to do is substitute in our values. Remember that D and Z are given to us in the question. Now you'll notice that what I've had to do here is to convert 5.81 times 10 to the 8 light years into meters. So I've multiplied this by a light year in meters. Now a light year is going to be the distance that light travels in a year, so we multiply the speed by the time taken, which is going to be 1 year. So the 365 times 24 times 3,600 is the number of seconds in a year. You'll notice that there's a 3 times 10 to the 8 on the top and the bottom of the fraction, so we can cancel those out to make this a bit simpler. So we end up with 4.415 times 10 to the power of 17 seconds, which I'm going to round to 4.42 times 10 to the 17, as the values given to us are to 3 significant figures, and that will be your answer. So in terms of marks for this question, your first mark will be for recognizing that the age of the universe is equal to the inverse of the Hubble constant. Your second mark will be for using the equation Z equals V over C. Now we've combined this as part of another equation, so that would still get us a mark, but in the mark scheme, it's detailed as actually using that equation and substituting the values into it directly. You get another mark for a calculation of D, which again, we've substituted here directly into the equation, but we still have made that calculation. And then your fourth mark will be for correctly getting 4.42 times 10 to the 17 seconds at the end. So 4 marks there. A typical quasar is believed to be approximately the size of the solar system, with a power output similar to that of 1,000 galaxies. Estimates, with reference to the inverse square law, how much further the most distant visible quasar is likely to be compared to the most distant visible galaxy. Key point here is that the power output is similar to that of 1,000 galaxies. So that's a multiplication factor that we're going to need to use. Now, if we're looking at the most distant visible quasar and the most distant visible galaxy, we're going right the way down to the limits of brightness that our eyes can detect or our measuring equipment can detect. So the power received from the most distant visible quasar will be the same as the power received from the most distant visible galaxy. So that's the first thing that we're going to write down, and that will get us our first mark. So both are at the limits of our vision or measurements, depending on what equipment we're using. So the power received from either will be the same. Now the intensity of a source of light obeys the inverse square law. So we can bring these two powers together and compare their distances. Now these intensities, as we said, they follow the inverse square law. So the power of each divided by the distance squared will be the same. So if we apply arbitrary units to the power of a galaxy and the distance of a galaxy, we can then scale up for the quasar because we know that power is going to be 1,000 of those arbitrary units. So we're using multiples of galaxy power and distance. So comparing these directly, we can see that the power of the quasar is 1,000 times the power of the galaxy, and we're trying to find the distance of the quasar squared in comparison to the distance of the galaxy squared, which we're treating as 1. So all we need to do now is rearrange to make d quasar the subject of the equation. So this will be the square root of 1,000, and this is where that inverse square law comes in, based on a power which is 1,000 times the size. So we find that the distance of the quasar is 31.6 times the distance of the galaxy. Now backtracking through the last couple of points, you wouldn't get a mark for mentioning the inverse square law, but you get a mark for using it. And your third mark will be for coming up with a factor comparing the distance of the furthest visible quasar compared to the furthest visible galaxy. So 3 marks there. Evidence to support the Big Bang theory comes from cosmological microwave background radiation and the relative abundance of hydrogen and helium in the universe. Explain what is meant by cosmological microwave background radiation and how its existence supports the Big Bang theory. So there are lots of different things that we can say for this question, but the first thing that we should say is about how the cosmological microwave background radiation is coming from all parts of the universe rather than one specific point. And that's going to be our first mark for saying that the cosmological microwave background radiation comes from all areas of the universe rather than a specific location. We know this because when the Big Bang happened, the universe expanded from one point, so the radiation that existed has always been in all parts of the universe and is expanded out with the universe. But it's that expansion that's going to get us our second and third marks. When the universe cooled enough, matter and radiation were able to decouple, and this is where that radiation comes from. But we should also mention that protons and electrons were able to join together to form atoms. And that level of detail will get you your second mark. Your third mark is going to be for talking about what happened to the radiation after the Big Bang and why it's microwave rather than any other part of the electromagnetic spectrum. So here we need to talk about redshift. So as the universe expanded, the radiation was redshifted, so it stretched, its wavelength became larger into the microwave region of the electromagnetic spectrum. You don't need to mention the electromagnetic spectrum, but it's worth including here, just to show that you know what you're talking about. So that's our third mark. So 3 marks there. Explain how the relative abundance of hydrogen and helium supports the Big Bang theory. Now the idea here is that if the Big Bang hadn't happened with high temperatures and pressures, there would only be hydrogen. But the existence of helium is because the high temperatures and pressures at the Big Bang, or shortly after, caused the fusion of hydrogen to form helium, just as it does in a main sequence star. So let's put this into words on paper. So shortly after the Big Bang, temperatures were high enough to fuse hydrogen to helium. That's going to be our first mark. This didn't go on continuously, obviously, because the universe then cooled down and that fusion stops. When the universe expanded and cooled enough, this fusion stopped. And obviously this was because temperatures weren't high enough for this fusion to continue. You don't need to go into any more detail than this to get this second mark. Your third mark is going to be for talking about the ratio of hydrogen to helium that was left over. So about 3 times as much hydrogen as there was helium, and temperatures were no longer high enough to fuse either of these elements into heavier ones, which would then alter the ratio further. So the fact that no heavier elements were produced suggests that the universe didn't get any hotter after that, unless we're talking about inside stars, like red supergiants. So that point made in that much detail will give us our third mark. So 3 marks there.